Welcome to Datamatics. Today, we will look at demonstration on how we deployed operational analytics for a leading glass bottle manufacturer. The client was facing several issues across their operations, like high inventory carrying cost, meeting market demand on time, efficiency of machines in terms of maximizing the ratio of packed bottles produced as against the total melted glass generated by the furnace. The plant had two furnaces, N2 and N3. N2 was shortlisted for an engagement on operational analytics. The furnace N2 has 5 machines with SKUs associated with each machine. The machines are designed to produce certain types of SKUs as per their weight, width, height, with a unique production process associated with each SKU. The project was focused to solve 2 problems, the first one being production planning, and second one was optimizing machine efficiency. With production planning, the objective was to forecast market demand accurately to ensure SKU production was precise. This required optimizing allocation of SKUs to production runs to maximize furnace draw while reducing production time. All of this while achieving monthly production targets. The second problem was to improvise machine efficiency and minimize defects by keeping machine parameters at optimum levels. This use case included tackling challenges such as meeting market demand, managing market priority, minimizing job change time, adjusting job run lengths as per Sundays and holidays. Data was extracted from various sources like monthly SKU sales data, production data, SKU forecasting data, and job change data. All of these aggregated and prepared for analytics consumption. With this use case, we targeted to deliver an easy-to-use demand forecasting solution and a quick mechanism to derive optimized allocation of SKUs with one-click scripts for each. This enabled the production and planning teams to orchestrate production schedule effectively. The client traditionally used market intelligence-based forecasting with accuracy and precision of less than 50%. Improvising demand forecasting, hence, was the first task towards production planning. Furnace N2 corresponded to 150 plus SKUs. We analyzed that the top 25% contributed to 81% of the business. This high concentration necessitated focused and precise demand forecasting of this 25% to ensure the overwhelming component of the business is effectively catered to. As a corollary, this approach also ensured meaningful return on investment, with inconsequential SKUs not getting undue attention, time, and energy from a resource mobilization standpoint. We ensured that sales data was first transformed into multiple time series for different SKUs, followed by necessary time series decomposition, stationary test, etc. Multiple methods like ARIMA, Holtz-Winter, exponential smoothing, etc. were used to predict futuristic sales. The predicted numbers were then coupled with already available market intelligence-based estimates with the help of optimally derived weights to minimize prediction error. We derived a prediction algorithm that provided a one-click solution script based on our programming. The pictorial representation on the screen provides a holistic understanding of the optimization model that was in play along with the production flow. Data comprising of demand forecasting, sales, and inventory are meaningfully linked and aggregated to ensure readiness and compatibility for analytical consumption and subsequent intervention. Based on the demand forecast, derived production target, and other associated critical inputs, subsequent allocation of production target is done at individual machine level. SKU to machine mapping and correspondence is then leveraged. To decide and determine the intricacies of the production flow in terms of sequential versus parallel run, appropriate sequencing of job runs, and other critical considerations. Sophisticated optimization algorithms and their ensembles are deployed to ensure that the optimization objectives are met. Production data was leveraged to identify and derive key production parameters like maximum draw per day by each SKU, estimated job run length for each SKU, identify opportunities for parallel job runs, arranging job runs to minimize the time difference of furnace draw and successive runs, arranging job runs by sequencing SKU basis, volume, and weight. All these finally helped derive a production planning sheet for coming month. Just like sales prediction, we built a one-click solution script to produce the planning sheet in quick time. Our demand predictions were significantly accurate as compared to the forecasting estimates by the marketing team. Overestimation of demand was reduced by 22%, while underestimation was reduced by 31%. This helped in reduction of business risk in terms of inventory carrying cost and loss of customer order. Optimized allocation of SKUs resulted in reduced turnaround time, reduced production cost, production of more number of SKU, lesser deviation between production and sales, and improved operational efficiency. With machine efficiency improvement, the objective was to reduce number of defects in the production run. To achieve this, we extracted various datasets like machine-level production run data, shift-wise rejection data, daily production reports, machine breakdown data, temperature and density data for melted glass, etc. for analytics consumption. We provided insights on optimum levels of machine parameters to reduce defects in the production run. Machine efficiency was achieved by minimizing loss in job change, along with minimizing defects in a production run. The methodology used to minimize defects involved several steps, like hypothesis testing to identify factors associated with rate of defects, statistical analysis to find out significant variables impacting the rate of defects, and finally, the data analytics model building followed by algorithmic simulators to arrive at optimal machine parameters, minimize defects. We listed 39 defect types, and from this list, we identified that only 9 defective types contributed to 83% of total defective items. Furthermore, these specific categories of defective items contributed around 4% of the overall production, thus impacting machine efficiency in a big way. Extensive statistical analysis was deployed to identify the relationship between machine parameters and a specific defective category. Melted glass density and various temperatures of melted glass were leveraged to find such relationships. The correlation matrix depicts the nature and strength of associations among the attributes under consideration. Regression analysis was leveraged coupled with Minimax algorithm to derive optimum levels of machine parameters. These optimum levels, combined with algorithm-based simulators, were leveraged to test different production runs. In the process, defects were successfully reduced to 2% from a 4%, leading to substantial cost savings in the large production environment. The notion of bivariate regression was systematically extended to encompass multiple regression approach, which resulted in more precise results leading to further reduction in defects. To conclude, with operational analytics, we identified multiple opportunities to improve operational efficiency for the glass bottle manufacturer. Major improvement areas included improving demand forecasting, reduced defective items, optimized production environment, etc. The overall approach opened up further possibilities of scaling and proliferation that potentially can have major financial benefits.